Okay, guys, thanks for being here today for our an evening with of the 9th of April. We have the pleasure of having with us Mathias, who has an interesting talk on deep learning. Big round of applause.
Thank you for having me. So yeah, like the talk is going to be about deep learning in general, and specifically about deep learning with a CNTK, which is the library I'm going to talk about, and CNTK and F#, because F# is a piece I personally care about a lot. So for those of you who don't know me, first, hello. Then my name is Mathias Brandewinder. You can find me on Twitter. You can find me in many places. I look like the guy on the right, like in all these places online. That's from Tintin, a big influence in me growing up. And the two things, technically or professionally, the two things which I care about or which are interesting to me, on one side is like I'm really interested in functional programming, specifically functional programming with F#. And on the other side is like I have a general interest in anything numeric, like mathematical oriented. So that can be machine learning, that can be optimization, that can be many things. So tonight it will be F# and machine learning specifically. Also, like as you probably, so I live in San Francisco. You probably picked up that I have a very strong Californian accent. In case it's not clear, so I'm French. I'm mentioning this because I tend to speak very fast, especially when I talk about things I care about. So if at any time I speak too quickly or simply you have a question, feel free to interrupt me. And if the question is great, but it would take a very long explanation, I reserve the right to say, this is a great question, but I will take it later. Deal? Deal. So the context for this talk is, like, where is this coming from? The first piece is I'm assuming that it's not controversial if I say that deep learning is a very hot topic right now. Like it's everywhere. People talk about self-driving cars, talk about like machines are going to solve all our problems with deep learning. This is apparently the thing to do. Might be true, might not be completely true, but it's an interesting topic. The second one is, so I mentioned F# earlier, like most of the work I do is on the .NET framework. And if you do machine learning or data science, like most of the action is not happening on .NET. It's happening typically on Python, maybe on Scala, maybe on R. So .NET is not exactly the hottest place for machine learning. And in particular, it's better than what people think it is, but it's not the hottest place. And in particular, for the longest time, like there was really no good solution to do deep learning. And so for me, this was a bit of a problem because I like deep learning, I like F#, I want to do both of them together. I would like not to have to pick one of the two poisons. So I was looking for a solution. And then about 6 months ago, I think, maybe a bit less, Microsoft released a library which is called CNTK. So CNTK is something very similar to TensorFlow. It's pretty much the same thing. And the thing which made me excited about it is the fact that CNTK actually has a .NET API. So for me, this is perfect. If I have a .NET API, I can use F#, I'm happy. And so this is what I'm going to talk about tonight is first like a bit of machine learning and deep learning in general, then talk about CNTK as a library, like what you have in it, how it works, and then talk a bit about my current work on making F# and CNTK work nicely together. So this is kind of my plan. So 3 parts. First part is I'm going to do a shallow introduction to deep learning. The shallow part is like, so I'm assuming that people in the audience are not necessarily deep learning experts. So I'm going to start with trying to talk about what is deep learning, why would this even work. I'm not going to go super deep. So it's a bit of a challenging topic to talk about because if you talk to mathematicians, it would be fairly easy to explain in a certain way. If I give a mathematician explanation of deep learning, it will be very difficult to relate to as a software engineer. So what I've been trying to do is like to essentially do a presentation on deep learning, which is explaining why it should work or why it might work, not going into all the details, but trying to lie as little as possible about the topic. Like I will not tell you all the truth, but I will tell you nothing which is blatantly wrong and it's overall correct. Then once we talk a bit about this, I'll talk about CNTK and connect like how this relates to the other part, like how do you use CNTK to do deep learning, and then I'm going to talk about using F# specifically to compose models and make easy the composition of deep learning models. So let's start with the shallow part, the deep learning shallow introduction. Enrico was foolish enough to give me a beer before the talk. I hope I hope this will not backfire. And so, before talking about deep learning, I'm actually going to start with a direction which has nothing to do with deep learning and progressively build up like how this connects to deep learning. So when I say something which really has nothing to do with deep learning, is like what I would start with is Donkey Kong. Because Donkey Kong is a great game, and it's like, why not start with Donkey Kong? Like people talk about burritos, about monads. I will talk about Donkey Kong and machine learning. And the reason I wanted to start with Donkey Kong is not the game, but it's really the part which is interesting to me is this piece on the upper corner. So this is an 8-bit game, and an 8-bit game is like 8 by 8 grids where you run the numbers. Like if you want to write a 1. You activate some of the pixels and so on and so forth. And so the problem I want to look at is like, what would I do if I wanted to render numbers on an 8-bit game? And so what I would do is probably something along these lines. Like each of the numbers can be plotted on an 8 by 8 grid. Each of them is essentially you have pixels, like 64 pixels, and some of them are really on or off, like active or not active. That's fine. And so one way to think about rendering numbers then is I can think of this grid as, say, lamps, bulbs. And I have like 64 bulbs. And what I want is I want the right one to light up. And I want like some of the pixels to be active, some of the pixels to be not active. In other words, is I'm trying to do something like this. I'm trying to build something like a circuit where I'm going to put on and off. If it's on, one of the pixels will activate, and otherwise it's not active. Not very complicated so far. To represent this idea of a switch which goes into a cable, which goes into a lamp, I'm going to use something a bit symbolic like this. I thought like you were so excited about the talk, because like, I'm a bit disappointed here. That's right. Thank you. So symbolically, I could represent it this way. What I'm doing with the switch is like I'm pressing the button, so suddenly electricity is coming in. So this is the arrow coming in here. And if the current or the power coming in is not high enough, the output will be 0. And as soon as it passes the gray line in the middle, like if I have enough electricity, it's going to go up. And I'm going to give a signal which is 1, which is active. So not active, active, enough power, not enough power. How would I use this? So now, if I wanted to render a 1, I would say this is not difficult. I'm going to put like a switch, so on or off, sends electricity to my activation gate, and then is like all I would do is like take 64 cables, plug, and decide like which ones are going to be plugged to a lamp. So here, what I did is I just put like 3 pixels which are there, like, just zoom them in. I have like 3 lamps. I want this one to light up. This one should not be alive. This one should not be alive. So I'm going to simply put 1 cable. This is all I need. I put 1 cable. The other ones are not wired. And now if I press on the button, the thing in the middle will light up. And if I depress the button, it's like everything is dark. So I'm fine. And I can render one that way. So that's one way to go. The one thing I don't like about this is that it will require a lot of hand wiring, because now I need to look at every lamp, every pixel. I need to decide which one has a cable, which one has no cables. This is a bit annoying. So one way, one slightly different way to do this would be to say, like, instead of wiring only the lights which are supposed to be on, I'm going to wire every single thing. So I'm going to have like from the entrance, I'm going to have like 64 cables. So in this case, again, for like 3 pixels, I'm going to now have a cable going here, a cable going here, cable going here. But what I'm going to do is that I'm going to have something which allows me to control how much power goes in. So in this case, I'm going to say, like, I have a cable here, but here I'm going to let 0% go through. So no matter what, it's like it will still be dark. This one will pass like 100% of the power. So when it comes in, when it's off, I get 0, 100% is going to be 0. And when it's on, it's going to be alive. And the one here is the same as this one. So maybe conceptually or like practically, what I'm doing is I'm doing something like this. It's like now I'm saying, like, I have an input, which is like on and off, and like I have 64 cables, and on each of them I have a volume button, which allows me to go from nothing to everything goes through. So why would I do that? Like the reason I would do that is like on one side, like something is more complicated, on the other side, something is more simple. The thing which is simple is like now is like I have 64 cables, the wiring is completely straightforward. Now I moved my problem to instead of deciding where to put the cables, I have cables everywhere, and now I need to decide like how much current I need to pass through. So that's I moved the problem a bit. But that being said, is like I think you can imagine how this would work out. I can now represent a 1, a 2, a 3, a 0, whatever I want using this mechanism with the same type of wiring. So this is what I would get. If I wanted to render not only a 1, but every single number, I would press a 1, and I have like all sorts of cables going through the thing. I have a 2. The wiring would be, everything would be wired, but I would have like slightly different positions for the activation things. And so with that approach, I can represent pretty much anything I want. Good. So now is like you might say like this is great, but like what are you talking about, and what's the relationship with machine learning? And the relationship with machine learning would be what I wanted now was like if I press 1, I want a 1 to show up. If I press 2, I want a 2 to show up. How about I look at the other problem? The other problem would be reversing the problem, and the question becomes: if I show you an image of a 1. Can you tell me that it was a 1? So I want to flip the problem and take it, instead of going from this direction to this direction, I want to go from the image to activate the right button. And so to do this, it's really not that complicated. It's like what I would need is I need to essentially reverse the cables. Instead of going from the button to the lamps, what I want is like I have an image now where things are either there is current or there is no current, and I put the cables the other way around. And what I would like is like something where if I put the right weights, like if I put the right power, then I would like I would like the answer to come off as this is a 1. That's so the first problem was going from a 1 to displaying a 1, and now I'm going from this is an image of a 1. Tell me it's a 1. That's what I'm trying to do. Good. And as it turns out, like this should not be that complicated, because like what we are really building here is like what we want is a filter. And the one way we could make that work would be by start to play with all the weights or with all the knobs. And what I would do is I would probably say like take the 1, start to move the weights so that like the current which comes off in the 1 goes up. And I would want also, like when I give you a 1, I would want the current which goes to 2 to go down. So I would want a signal which is very strong for the correct answer, and a signal which is very weak for the answers which are not correct. And if I take that particular example, I could do something like this. So if I look at this image and I'm trying to predict if it's a 1, that pixel is not going to be very helpful, because that pixel is always dark. So it's like it's not telling me anything interesting, so I will probably keep the weights very low, like 0, because it doesn't give me any information. The light on top is also dark all the time, so if I see this, it's like I don't know anything, it's not helping me. But when I see this particular pixel active, like this is a good indication that this is a 1. And so in this case, I will put actually some weights which are high, and as a result, is that when all the pixels which represent the 1 are alive, I will get a very strong signal which flows back. So I could start to essentially do the sum of the signal here, and I would say I see this, and I see this, and I see this. All these things are on at the same time together. This looks a lot like a 1, and so this is kind of what the model would look like. So what I described is like so the process you would do, the process you will see in a machine learning library is essentially going to do this. Is like I'm going to take an image. I know the image is a 1, so this is what I had, and I'm going to learn by the overall view is like I'm going to give my my system, or like my thing, like examples where I have an input and I know what the correct output is, and so I'm going to give you like one image. I know it's a 1, pass it through the system, compute the output, so it looks at what it tells me for 1, for 2, for 3, for 4. And start to move the weights around so that the signal goes up for 1 and goes down for the whole rest. Then I'm going to take maybe an image which is a 3, pass it in, and start to move the weights so that the answer is high for 3 and low for the other ones, and so on and so forth. And you would like repeat and repeat and repeat and repeat. And if everything goes according to plan, at some point you will have weights which are going to give the correct answer for the correct input. So this is and in essence, like this might sound like silly, but this is exactly what machine learning libraries do. It's like you give them examples, and they will iteratively tune themselves to get closer and closer and closer to the answer you want to observe. So good. So this is like a very hand-wavy explanation, maybe for what a machine learning model would do. Now, I would like to look at a question, which is the following. So exactly now what I'm building is something like this. What I'm really saying here is I'm trying to build a system where if I give you an image, so it could be one, could be two, could be anything, and I want to build a system which is going to predict either one or two. And here I should have like some weights or some which correspond to each of the pixels. So I'm trying to learn a weight for this and a weight for this, so that they multiply the right input to give me a strong signal out. And the question I'm interested in is like, if I did this right, what would I expect the weights to look like? And as a first pass, so what I would expect to see is something along these lines. First, if I give you an image which is a 1, I would, as I showed a bit earlier, like I would expect that the things which are not really useful, like all these things should have like very low weights. So here I'm seeing weights which are left at 0, because like this is not helping me decide if it's a 1 or not a 1. The filter, the part which I care about, is in the shape of the 1. So overall, I would expect the weights to somehow match the shape of the input I'm passing in. Same thing for the 2. Now, as you might see on the screen, is like some of the weights are actually in red. And they're in red because this is actually the weights I would expect to be high. And here's the reason. Now, imagine for a minute that I see an image and I see maybe a 2. And so that, say, that pixel is on. So I see this, and so we say this is definitely part of a 2. So this should be a high weight because this is showing me that this is a 2. The problem with this is that that pixel is also active in the case of the 1. So if that particular goal or that particular pixel is active, it's not really telling me anything about whether it's a 1 or a 2. It could be one, it could be the other. So what I represented in red is all the places which are unique to a 1 and not present on a 2. So you should see something like this, like the bar on top red is on the 1 and not on the 2. The pixel completely at the top on this one should be not active because I don't really know. This one here should also be dark because it's both on the 1 and the 2, so I don't know. So what I would expect is I would expect to see big weights for the things which are unique for the 2 and not present on the 1. Does it make sense? So taking that thought and going a bit further, you could say, but is that I could actually find a model which is even simpler, and I could do something like this. Because really, like if I see a 2 and I know that this thing is on, I know it's a 2. Like I don't need anything else, right? It's like this is the, if I have this, like this is not part of a 1, so this is sufficient. Similarly, like if I see this pixel, another one is like I know it's a 1, it can be a 2, I'm done. So that could work. I mean, that works. Like there is just a bit of a flow with this approach. It's like that model is really not robust. Like if you have any form of noise in the input, like maybe the cables are flaky, a problem I'm familiar with now. Maybe like for whatever reason, like the input is not very robust. Then is like if you get a bad signal on that specific pixel, your prediction will be entirely wrong. That's not very good. So you are relying on a single point of information to make your decision. So this is why the expectation would be, even though you will get the same result with a single pixel in a perfect world but with no noise, it's not going to be a very good model. And so you would much prefer to have weights like this, so that like if one of the inputs is flaky, you still get a strong filter, which is still going to work. So good. So this has a name, like it's called the perceptron. This is one. I would call this like shallow learning. Shallow being because I have only one layer between the input and the output. Like there is just one filter and nothing further. So I call that shallow learning. And in the end, it's like machine learning or like deep learning models are going to be about like giving examples and find weights which give you the right answer given If you give it examples, it's going to try its best to find weights which are going to give the answer you expect. Another way to look at this is like, so I use the analogy of like lamps and cables and all of this. One way you could look at this is like what I'm really trying to do is I'm trying to compose a circuit or a board. I'm giving like a bunch of components. I'm saying I'm going to use a component of 8 by 8, a component of 8 by 8. Here are the cables. And I want to give that particular circuit or that particular computer a set of examples, and I want it to learn to do the right thing. So it's like one way to look at this is that we're really building something like a circuit board. We are wiring it up, and we want this to tune the wiring to produce the right answer. So that's not the only way we could build this, though. We could, so far what we have done is like building a circuit with we have 8 by 8 inputs. I'm going to use 8 by 8 filters to get the output. I could slice the problem a bit differently. For instance, one thing I could say is that if I took a 2 is like 8 by 8, 8 by 8 is really 4 by 4, 4 by 4, 4 by 4, 4 by 4. I can break it into smaller components, and I could say that instead of taking one unique filter, I could say, try to recognize this, try to recognize this, try to recognize this and this. If you see these 4 things together, it's probably a 2. If you see this, but not this, or this, and not this, like this might be a 3, for instance. So I might have like small shapes, which I can recombine into bigger shapes. And so this is what I'm doing here, is I could build a circuit which would be, instead of big components, I could build small components, like 4 by 4, 4 by 4. Now I would pass this on the image and say, do you see this here? If you see this here, you're going to get a signal which is 1. If you don't see this here, it's going to be 0. So now if you see this here, and this here, and this here, and this here, you're going to get 1, 1, 1, 1. And now out of this, I should be able to say, like, if you see this is on, and this is on, and this is on, and this is on, then this is a 2. So instead of taking one big model, I can start to break it into smaller models and try to combine the output of small shapes into bigger shapes. Like help it like recognize smaller patterns and let it aggregate or recognize like bigger features or bigger patterns. So this is maybe slightly more, it's simpler and more complicated. It's like we're using like smaller circuits or smaller components, but we are, instead of doing one big component to do everything, we're trying to combine them so that we have like a first filter, and the filters are then combined into other filters, which are combined into other filters, and so on and so forth. What I'm describing here is something which looks like this. Like first, I can do more of this. Like instead of just like one row, I could start to have filters or sensors and plug them into other sensors, and so on and so forth. So here I could say I could have like 4 shapes I'm going to detect, or maybe 50, maybe 200, maybe 1. Like that's not usually important, but they have the same general shape. Each of these is going to detect something in the image. And then is like each of these is going to have an output, like I saw this or I didn't see this, I saw this or I didn't see this. And now you can take all of these and combine them into another row of sensors. And you could, so this one and this one and this one would go to this one, all of them would be plugged to this one, and so on and so forth. And you could keep having more and more and more layers of this up to the answer you want to get at the end. This is where you go from shallow learning to deep learning. So what we're doing here is we are first like we're composing. We're doing a model which is composed of multiple layers. Like the first layer is going to be something like 20 filters, 20 recognizing 20 shapes. The second one is going to be plugged with maybe 4 of them, and so you're just stacking up like filters on filters and filters. So this is what people call deep learning. Is like you have like more layers. And the idea being like instead of trying to detect big patterns from the beginning, you're trying to detect small patterns in the beginning, aggregate them into bigger patterns, which is so the computer will recognize maybe small shapes, and then is like it will learn by itself to recompose the shapes into bigger shapes and recompose them into bigger shapes up to the moment where it picks up that it's a 1, it's a 2, it's a hot dog, it's a bird, it's whatever you want. So it's a bit hand-wavy, but like this is pretty much how it works. So recap is like deep learning models are composed of layers. You can think of layers as arrays of filters, like and the way things tend to work is not tend to work. The way things work is that you are essentially building up a specific architecture or a specific structure for a model. You're wiring everything together, and then you're going to feed like a lot of examples and let the model learn the weights which make the model work. Other questions so far? Once.
The input for the layers is the output of the previous layer.
That is correct.
Okay.
Like in the first level, it's going to be just your input, and afterwards, like if I look at this one, the input. So essentially, what you're going to do is like when you work on creating layers, is like the first layer is going to be filters or sensors or however. Each of them is going to give you an output, which is going to be somewhere between 0 and 1 or something else. And then the next layer, like every one of these is going to be connected to all the outputs of the previous one. And so this one will be taking the inputs for all of these, this one same thing, this one same thing. So they're all plugged together. More questions? It's amazing how well this trick works. Going once, twice. Good. So now, now that I explained a bit like how this might work and like why, how and why this might work, I want to talk a bit about CNTK. So CNTK. So first, what is CNTK? So CNTK is one of these wonderful acronyms from Microsoft, and they really have a. This one is pretty nice. So CNTK obviously stands for Cognitive Toolkit. This is what CNTK is, and so this is a project which is like public, I think, since maybe 6 months. Is open source. Like if you go on GitHub, like the whole code is there, all of it. Like GitHub, Microsoft CNTK. They take pull requests, they take contributions. Some of the reasons I cared about it. One of the reasons I cared about it was that it's used internally by Microsoft since a while. Like this is their library. They use also TensorFlow in some places, but CNTK is what they use for projects like Skype, like for Cortana on Xbox. So they use it on a couple of major projects internally. And for me, this matters because historically, I've seen cases where you have a library for Microsoft. It's like, you should be using it. It's absolutely great. And then 6 months later, it's like, what library? It never existed. And it's like you spent like 6 months learning something and it's gone. So if they use it for Bing and all these things, like I have good hope that in 2 years or 5 years, it's still going to be around and they have an interest in investing into it. The second reason, like CNTK is interesting. So I mentioned that at the end, like I mentioned that it's similar to TensorFlow. Like pretty much the library do the same thing functionally. One of the technical reasons like CNTK is interesting is I can build a model and I can run that model on a CPU, so on my local machine. I can also run it on a GPU on my local machine, which is pretty nice. And I can also run it on multiple GPUs in a distributed fashion. And it was built actually to do that. So that's one. That's a big, and probably that's a big plus compared to TensorFlow. Like TensorFlow, you can run it on a couple of GPUs, but it doesn't scale very well. And CNTK has been built to scale on a large number of GPUs. So I'm probably not going to need farm of GPUs for my own usage, but like if you really have like a lot of data and very big models, it's built for doing that. Another argument in the same direction is like the data set I work on are typically fairly small, but I'm assuming that if it works for Bing, I know Bing is not the biggest search engine, but still like the volume of data they're getting is like probably billions of times bigger than what I will ever see in my life. So like if it works for them, it's like I have a good chance that it's working for me. Technically, CNTK has a C++ core, so the whole gory part, which is doing the computation, is C++. And on top of it, you have a bunch of languages you can use. Like if you want to work with C++, it's possible. If you're a masochist and want to do that, it's like, please knock yourself out. But you have also a couple of other languages on top. So you have they have a good Python API. Keras runs on it. You have something called BrainScript, which is like a custom scripting language they did, and you can use it from .NET. So .NET being they designed something which is working really, which is working with C# and like any .NET language like F#. So that's one of the reasons I cared about it. Now is like so this is what CNTK is. Like the question would be like so that's great. What do you do with it? So it's a library, and given the what I described before, is like if you want to do a deep learning model, you're going to need a couple of things. Like so you need to define a model. So I need to what I described in my networks, where like inputs going into sensors, doing computation, and so on and so forth. So CNTK allows you to define how the input and output are connected. Like you can define functions which go from the input to the output. So freeform, you can build whatever model you want. If I want to train my model, I need to be able to get data from somewhere. So in the library, you have a bunch of readers, like readers from text files. You can work from in memory. You can work. You have readers for images. So you can easily plug so you can easily say, like, here is my data. I want you to feed the model with it. If I want to learn, I will also need to learn weights. So this is what. Yes.
Okay. So in the code, there exists importer from model trained with TensorFlow, and use that model with CNTK.
I don't have a direct answer on this. So I have two half answers. So it's almost an answer. The first one is there is a library I'm going to mention later called Keras. So Keras is a Python library which allows you to create a model and essentially do the first part, mostly the first part. And so Keras will you can take a Keras model and you can run it on TensorFlow and you can run it on CNTK. So that's not quite the same as what you asked, but like the indirect answer is like instead of doing a TensorFlow model, you can do a Keras model and run it on multiple platforms. The second one is like this is an area I'm not familiar with, but I've seen the term Onyx pop up quite a bit. And as far as I understand, it's like a specification for models, which is supposed to be like a standard. And I believe like TensorFlow and CNTK either support it or are working on supporting it. But like this is the part where I had like maybe one half answer and 120% answer, something like that. So that's the best I have. Like otherwise, I don't think you can take a model from TensorFlow and run it on CNTK and vice versa. Good enough?
Because there exists a bunch of models portrayed with TensorFlow.
Oh, I see. You already have TensorFlow models. Yeah, like and are they written direct? What are they written in? The models are written in Python, or?
I don't know how they are written, but I know that there exists some pre-trained models.
So I don't want to tell you that it's not possible, but I don't know for a fact that it's possible. Best I have. So yeah, I can specify how the input and output are connected. I can specify. I can tell it like here's a file which is a text file and read it. I can learn weights, so that's the learning part. So you can say now I have a model, I have data, like learn. And you have once you have learned a model, is like if you want to do something interesting with it, you probably want to use it in a program. So you can save your models and you can reopen them and like use them to make predictions. So this is what you get out of the library. The main pieces, the core components in the library, these are I think the main ones. So the core component is something called an ND shape, also called a tensor. I'm going to talk in a minute on what a tensor is. Like it sounds complicated, and once you realize that what it is, it's actually not really complicated. But I'm going to explain what a tensor is in a second. Then is like what you do is like when you build a model, you're really building a function which is taking input and giving you an output. So the core element is like a function. Like you have this notion of a function, and a function can take like 3 types of arguments. I'm also going to talk about this a bit more. Arguments to a function can be input variables, can be parameters, and can be constants. So I'm going to talk in a second on why you need like 3 inputs and not 1 type. Then you have trainers. So a trainer is like simply something which will take a model, take data, and like train, not too complicated. And finally, you have on the readers. So you have a bunch of readers out of the box. And specifically, you have a term you will see maybe is like mini-batch readers. So what a mini-batch is the following. If you have a small data set, you can afford to read everything in memory, and that's fine. If you have like terabytes and terabytes of data, you cannot read everything in memory. This will not work. So a mini batch is the idea that you want to look at your data set and you want to give me like 100 examples. And then give me another 100 examples, and ideally give me something a bit shuffled or a bit random. So this is what a mini batch is. And the mini batch readers are going to allow you to plug to data and then read by batches of 100, like somewhat randomly in the data set without reading everything in memory. So these are like the core pieces in the library. So now I mentioned like all of this is using tensors, and one question might be you might have is like what the hell is a tensor? And a tensor is like a very fancy way to say like I'm working with arrays. So what a tensor is is an n-dimensional array. So sometimes your data is just an array of numbers, and this is fine. If I take something like an image, is like it's a square, so that you would represent it as a two-dimensional array. Maybe this would be a two-dimensional tensor. Maybe you have an image which has colors. So in that case, it will be RGB. So now I have 8 by 8. I have the red, I have the green, I have the blue. So now I have something like a cube. I have 8 by 8, and I have like a first layer which is going to be red, second layer green, third layer is blue. Maybe you have a movie, so a movie in color. So in that case, you would have probably a 4-dimensional tensor where you have like 8 by 8 by 3 by the number of frames you want to look at. So the point is, so really like first, like these, so in CNTK, they're called like ND shapes, like in n-dimensional shapes. And these are really like n-dimensional arrays where you can say like this is how big they are. And the thing which is convenient is because everything now is becoming like an array, it's kind of easy because all the inputs are arrays, all the outputs are arrays, and so it's pretty easy to compose expressions together. Like you're keeping the same types, like array to array to array, so it's easy to compose things together. For instance, if I took the example I was describing before, so what I'm trying to build is I'm trying to build a function, and the first thing is like I would have an input which would be an image. That image would be a 2D tensor, like 8 by 8, and you would describe it as a tensor of dimension 8 and 8. So it's like it's an array of 2 dimensions with 8 elements and 8 elements. The weights are also 8 by 8, so that would be something like a 2D tensor with dimension 8 by 8. If I look at the output here, I could do it multiple ways, but I could have like a single value, like it's either a 1 or not a 1. In that case, that would be a 1-dimensional tensor, like it's an array which is going to contain one single element. So this, the tensors allow you to represent a lot of data structures that way. So now, what I want is like I want to use the input and the weights to compute the output. So I could do this. One way I could do this is like through code. And if I did this through code, I would really say something like this: I really have a 2-step process here. I have a first process where I'm going to take all the inputs I have, and I'm going to look at the corresponding weight. So the process I described before is really saying that take that pixel on top, multiply by the weight on top. Take the next pixel, multiply by the next, and sum all of this together. So what I'm really doing is I'm saying that take the input, grab element 0, 0, multiply by the weight 0, 0, plus take the input 0, 1, weight 0, 1, plus, 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 plus. And so this is giving me how strong the signal from this filter will be. And the next step here will be, now that I have an output, what I want to know to get the prediction is like, is this active or not? And the way I could do this would be to say, if the output I got here is greater than a particular value, then the output is going to be 1, otherwise it's going to be 0. So I could also represent it this way in a fairly straightforward manner in code. And I could write it out as a straight code, and I would say like a model in that case would be input is an array of floats, weights is an array of float, threshold is a float, and I can just write code which does this. There would be no problem with this. In the end, this is what you want. Like this is what your prediction model will do. So the problem I want to revisit now is like, why do we have parameters, input variables, and constants? And the reason is the following. Like this is what you would want as a final implementation of your model when you have learned. But now is like the model, the algorithm will have a bit of a problem if you just give it something like this. If you just tell it, I have inputs, it doesn't know what it's allowed to change. Like normally, if I get an image, the image is the image is the image. Like I cannot change the input I get. The input is the input. What the algorithm should be allowed to change is the weights. Like this is what the algorithm is allowed to modify. And so for that reason, is like you need to have a bit of a separation on different types of inputs. Like you have inputs which are this is what you see, inputs which are this is what you're allowed to modify, and constants would be like a special case. And so in that particular case, I mentioned that you have inputs, parameters, and constants. So an input variable is like the thing you're getting and you cannot change. Like this is an image, this is what you have. Parameters is what I call weights. So parameters are the things which the model can actually tweak to get an answer which is better. And so as a result, is like when you build a function, you're going to have to be a bit explicit on like what is the input and what is the parameters. Questions so far? One, twice, thrice. So now it talked a lot, and I showed slides. So slides are great, but like I want to go a bit into code and show you how that looks. So I'm going to go to VS Code. And the first thing, yeah, actually before doing that, is I have a couple more slides. Like I lied. The one thing I'm going to do now is like I described the problem I was trying to do, which is so it's a bit of a fake problem, but I'm trying to recognize a 1 from a 2 on images which are 8 by 8. So I'm going to build an e-model to do that with CNTK so that you can see a bit how it looks. And the goal is going to see like if it actually works out. And the one difference, what I described initially was like I could build that model with the 2 specific filters. One filter which is going to recognize 1s and one filter which is going to recognize 2s. I'm going to make it even simpler, and I'm going to use one filter by using a simple trick. And so the trick will be like, what I'm going to do now is that instead of having weights which are just positive, I'm going to use weights which could be positive or could be negative. And so if I do that, what I would expect, essentially, this is like the 2 pictures I had before on a single filter. The yellow ones are the things which were for 1, and the blue ones are the things which corresponded to the 2. And so what I'm saying is like if my model worked, I would probably expect something like this. I would expect like very positive weights here, because this is going to recognize the 1. I would expect very negative numbers here. This would be for a 2, and so this would give me an answer which is going to be either very positive, it's a 1, very negative, it's a 2, and something in the middle is like, I don't really know, it could be a 1, it could be a 2, you tell me. So let's build that thing. It's big enough, even for the back. So I'm going to start with first, like, so I'm in VS Code, going to use F#. And so my goal, actually, that was one of my goals, is like the initial CNTK library was designed like on C#, and all the examples were like using console apps and all of this. And it's like, this is great, but I don't really want to work with console apps. I want to work with scripts. So my whole goal with working with CNTK was to make it usable completely from the scripting environment, completely from VS Code. So that's what I had. I've been working on this, and it's like there is a NuGet package. So the NuGet package is version 0.1.3. So there is a strong hint there that this is work in progress. And like take it, use it at your own risk. Like it's not completely fully polished, but it works. And the other point is like to use CNTK, I don't need to install anything. Like the only thing is like pull the NuGet package and it should just work. Like so this was my goal. So first thing I'm going to do is like I'm going to get like my NuGet package. So I already downloaded it. So I'm going to just get the CNTK package, and I'm going to open CNTK. I'm going to open a couple of small things, so not super important. One thing also, like a heads up, like first thing I'm going to show is like the experience like with no polish. So it's going to be pretty rough, and it's part of the point. Is like I want to show you like out of the box, like CNTK is using very low level components, and this is not quite what I want. So it's like some of the code will be ugly. I'm aware of it, and it's part of the point. And then I'm going to show you what I did to try to make that like not ugly. So if I want to learn, is like first I will need some data. So first thing I did was I created a data set. So I want to have 8 by 8 images. So it's like essentially I did something like this. Like I'm creating a 1, which is like a 0, 0, 0, 0. So it's either 0s or 1s. So it's like the 8 by 8 images I showed before. I did the same thing for 2s or 0s. I can't remember what I did. And I created the following data set. So this is like big data all the way. I have like 64 images, like a huge data set. And so it's a pretty artificial example. It's like small, but the one thing what I created was I created like 32 images of a 1, 32 images of a 2. Because I'm an idiot, is like I should probably have done 0 and 1. So it's like now if you see a 1, it's a 1, and if you see a 0, this is actually a 2 because it's not a 1. So it's a bit confusing. It was not exactly the best choice I made, but like it works. So now I have like, and you might notice as well. that in the data, so this is like one of the formats which CNTK supports. So this is saying like the output I'm trying to predict is going to be labels, and I have pixels. And I also added a bit of noise to my data set. So for instance, the first row is going to be 0, 0, 0. And some in some images, I just put some randomness so that I flip arbitrarily ones and zeros so that I have a bit of noise. So here's like 32 slightly noisy ones and 32 slightly noisy twos, which are really marked as a 0. So this is what I have to learn. So let's go back to the script for a sec. Create this, and this is fine. And so now my goal is going to distinguish, like, is this a 1 or is this not a 1, which would be a 2. So as I described, is like the first thing, I'm going to build a model. And so to build a model, I'm going to create two things. I'm going to create an input variable, like the data I'm going to use to make my prediction is going to be an input variable. I'm not going to really go into the details, but like instead of making it 8 by 8, I actually made it flat. So I'm saying like what you can use here is that you will get like 64 pixels. And these pixels are going to be floats. So now it's like I have an input variable. Similarly, I'm going to create weights. Like the weights are the things I'm going to want to tune, which my model is going to learn. And here I'm saying like, now this is not an input variable. Now this is a parameter. And the parameter is going to be also 64. It's also a float. There is a couple of technical details I don't want to go into, but like same idea. Like I have like 64 values as an input variable, 64 values as a weight. So now I have this. And now I should be able to create a model. And so my model is going to be something along these lines. So my model is going to say, take the weights, take the inputs, compute the product. So this was like weight 1 times input 1 plus weight 2 times blah, blah, blah. Then I'm going to, so this is the product here. I'm going to add a constant to it, and I'm going to pass it into a function called a sigmoid. So it's like, it's slightly more complicated than what I described before, but essentially it's the same. I'm multiplying the weights by the inputs, and I'm passing it to an activation function, which is slightly more complicated than the threshold I showed you. So couple of comments here. First, the thing which I'm getting now is a function. So it's like it's a function which I can train. Second one is like here I'm using CNTK lib. So CNTK lib is what's coming out of CNTK. So I can do CNTK lib dot. And if I do that, what you see here is like the library out of the box is giving you like pretty much all the math you will probably need. So you have absolute value, you have like sign, you have like plus, minus, multiply, all of these things. So this is nice because like these are all the operations you need to work on tensors. So you can start to build arbitrary models on tensors. And the reason this is nice as well is like that library is built so that whatever function you build, you can run it on a CPU, on a GPU, on a GPU. So it's like if you write it once and use that library, it will run on all these devices for the learning. So this is convenient. And if I look at a function like model dot, I can now access things like the arguments. I can access the parameters. Where are the parameters? And I should have the input somewhere. And I can save and I can load. So all of that. Yes, you can. It's a bit, you can like, you can, but it can be painful. What you essentially, because like when you create tensors and when you create all of this, like they're going to be named. You can give them names, or some of the names are going to be. If you don't give it a name, you're going to get a name like variable 1, variable 72. But you can ask in the function, like, give me the parameter named this. Get it out and see how it looks. It's possible. It's just ugly as hell, at least on the .NET side, but it works. The other piece I need is I need the output, so like what I'm trying to predict. So this is going to be a signal value. It's going to be an input variable because I'm going to read this from the file. And now is like what I need to do. I have my model. Now I need to learn it. So this is the part where things get pretty ugly. So I'm going to, essentially all of this is going to say like this is the model I created. This is what you define by good, not good. So this is called the loss function. Like this is going to, every time it computes an output, it's going to use this to say, is the output good? Is this what you expected or not? So in this case, what I'm saying is that I'm trying to compare the label, which was 0, 1, with what the model predicts, and I'm going to take the squared error. So it's like if it's the same, it's going to be 0, and the further apart it is, the bigger it's going to be. So this is some annoying tuning. So this is fine. Like now is like I have this thing which is also ugly as hell. I'm going to say like what I want you to learn is I want you to learn the parameters of the model, take them all, and this is what I want you to learn. Looks awful. I'm going to create a trainer. So now the trainer is going to be something you can train. So I gave it the model. I told it like what is it that it was trying to optimize, and I told it like what it was allowed to change to get to that result. So now the next step is like I have a trainer. I should plug it to the data. So here we go. Data reader, like more ugly stuff. So I'm going to a point. I have my file here, and my file, if I remember, had like labels and pixels. So I need to tell it like look at these things and put them somewhere. So this is what we have here. I'm going to say like the streams are going. You're going to find in the stream something called pixels, which is going to have 64 values. These are my pixels, and I'm going to have labels, which is going to be one single value. So let's get it. Here we go. And now is like now I can point it and I can say, great. Now look at the file which is called images, which is the one I had. Use these streams and create batches by just repeating, like go over the file infinitely for as long as I tell you to go. So now it's like I have batches. Now there is a bit more ugliness. Here I'm going to tell it that I want to run on the CPU. More ugliness, a bit more ugliness. So this is really like, as I said, like out of the box is like it works, but it's really like step after step after step after step, not fun. We're going to do better in a second. But now is like it's all set up and I can start learning. So I'm going to do that. So here what I'm going to do is I'm going to launch it. And here like it's starting to learn. So what I really told it to do here is like I want you to run 1,000 times over the data set, load it, adjust the weights, load it, adjust the weights. So first like get a mini batch, like get 64 values, and then train it and print out the result, like print out the evaluation. This is what I did here. And what you will see is something like this. So I'm reading and learning and learning and learning. And it's like in the beginning, like the numbers I'm getting are pretty high, which means like I'm making like pretty large errors in the prediction. Like in the beginning, it's on average, it's off by 0.3 when the numbers is between 0 and 1. So it's like pretty much like a random toss. And you can see that first iteration, it goes down, the loss goes down, and at some point it's getting close to 0, and it's getting closer and closer to 0. So iteration after iteration after iteration, the model is getting better and better and better at predicting the data. So now the last thing I want to do here is the following. What I want to do is like I want to take this, and I said that the weights, I told you how the weights should be looking. Now I want to actually do what you asked me if you could do, is like I want to get back the weights out of my model and I want to visualize them. So I'm going to do this right now. I'm not going to comment the code above, like it's essentially just looking at the data and trying to get the numbers out. And I'm going to go very old school. And so this is like WinForms, because like WinForms is the technology of the future, and because it was the easiest thing to do. And so what I got here is that I got out of my model the weights which the model had. And so I see like 8 by 8. Everything which is dark is like things which are like not big, like not high, not very positive, not very negative. So this is telling me that when it's dark, it's like things which the model doesn't think is useful. Things which are like yellow or like bright red are things which are very positive, which should be markers for a 1. And things which are bright blue, the brighter it is, the stronger it is for the 2. So these are very negative weights. And what I predicted is like I should see a shape a bit like the 1. And arguably, like I'm seeing that. Like, it's not perfect, but I'm seeing like the triangular shape I was describing here. At the outside, I'm seeing that the shape of the 2 is here the way I described. I even said that that bar should not be very strong because it's in both. So it's still showing a bit of color, like it's not perfect because there's some noise. But overall, I hope that you will agree with me that the shape I'm getting out of this is pretty much what I expected to see. So it's not only is this working at making predictions, but like it's working more or less the way I described it with. Questions on this?
How much did
What?
how much did the
This was super shallow. Like this was like a 8 by 8, and that's it. Like yeah. Yep.
Do you know if the CNTK comes with some visualizer? Because we did some custom.
Yeah. The answer is like yes and no. So the answer as the .NET part, no. On the Python side is like I think it's possible to use some of the same tools you use with TensorFlow, and so you can actually do some visualization on it. Like correct. I think it is on the Python side, but I haven't tried it yet. So it's like I think it is. I won't swear. Like if you don't find it, like don't blame me for it. Yeah.
There was a lot of noise, or
quite a bit of noise. Like and it's yeah, like you're saying it's not great. You're not impressed. Yeah. I mean it's not perfect. I also didn't do that many iterations, and the data set is pretty small. I don't know. Like the overall is like this one was like more to show like that overall. I think it's probably about the noise, because I think I'm switching like something like 5 to 10% of the pixels on each image. So it's because I have only 32 examples. Like there is quite a bit of noise in there. I would say that's probably why it's not better than it is. It also looks worse on the screen than here. The other reason also you get something a bit messy is like normally like the way you initialize a model is like the weights, you're not going to put them at 0, because if you put them at 0, like long story short is like it would not learn anything. So what you typically do is you put all the weights on random values, and so like the weights I start with are not necessarily very good, and so I might have like to run it a couple of times to get something better. But like there is half of the noise is like my own data, and there is some noise coming from the weights as well. So yeah, like what I predicted is like something that I would expect something like this. What I'm getting is like not exactly what I predicted, but like pretty similar. Like this is a not a proof that it works, but like at least it's not obvious that I'm lying. Like yeah, what I'm going to say. So this is useful. This is nice, but I mean it's nice. I'm saying it's nice. It's actually not nice. So it's like what I really want is like what I described in the beginning. I'm going to show you now like the type of work I've been doing to try to make CNTK like less awful to look at, or like a bit more convenient. And so the point here is like what I did was I complained at every step, like this is not nice, this is not nice, there is a lot of noise. And so what I don't like about, so what I really like about CNTK is like there is a library which works. I will take a horrible code which works over beautiful code which doesn't, so this is good. Like I like that. The part I don't like is like the code you get out of CNTK is like super low level. And like in the beginning, what I described was this view where you do models by, you do an architecture, you compose layers, you put these blocks together, and then I show you code where it's like, hey, here is some sand, here is some water, go build a house. Like it's a bit too low level. So, and what I want is like, I want to compose layers and say like, put 5 components of that type, put 7 components of that type, plug them together and go. One thing I mentioned a bit earlier was Keras. Is like, so I've been looking a bit at a library on the Python side called Keras, which is a domain-specific language which allows you to define at a very high level. I want a layer with 10 elements of this, 5 elements of this. I want to plug them, go. So what I wanted was to do something a bit similar to Keras on the F# side with the CNTK. So it's still work in progress. So you saw that there is a NuGet package. Some of it is done, some of it is not done. So what I have worked on mainly is what people call a sequential model. If you take, in general, machine learning models, they could take very complex shapes. Like you could have something which is taking not one tensor with multiple inputs. Like you could have multiple things you want to put together. You might want to build like multiple layers in parallel and then recombine them together and then get an output. So this is a fairly complicated expression to build. Like it's getting hairy quick. On the other hand, is like these are like completely general models, but like most of the models I've seen are fairly straightforward. And it's like here is an input, transform it, transform it, transform it, transform it, done. This is what people call a sequential model, where like you have a single input, which is a single tensor, and you apply a first layer, a second layer, a third, fourth, up to the moment you have a single output. So this is what I've been focusing on. And this is, I've been focusing on this also because like this was easy to think of as an F# person, because this is like a pretty straightforward pattern from F#, which is a model should be something where I take an input and I want to pipe compose it with a pipe and apply a transform and apply another transform and so on and so forth. And so what I was trying to replicate is that can I do this for CNTK? So let's do that. So what I'm going to show is like a data set like some of you are already familiar with. That's the NIST data set, which is a data set of handwritten digits. And our goal here is not going to be recognizing 1 and 2s, but like recognize 0 from 1, from 2, from a 9. And the data set is like a lot of data coming from humans writing on letters, numbers, and they have been scanned. And what I'm going to use here is, so the first piece I built in the layers is like what's called a convolutional network. So I'm not going to go entirely in detail, but the idea of a convolutional network is like, if you recall earlier on, I showed how you could have like different filters, which are going to recognize a certain shape and a certain shape and a certain shape. This is what a convolutional network does. It's like it's going to compose like typically 3 things. One thing is a convolution, so that sounds like very fancy, but what a convolution is it going to be a pattern of maybe 4 by 4, and that pattern is going to be scanned on the entire image, and the model is trying to see like, do I see it here, 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 here? And so it's looking for certain patterns in the entire image. So you want a layer called the convolution, and what you would want is you want to say something like, I want a convolution of 4 by 4, and I want like 10 filters, 1 filter, 27 filters. The second type of layer you have is activation. So activation is like, I showed you a sigmoid, we saw something which was like threshold 0 and 1. So there are various ways you can just tweak this to take the input to the output. And the third type of layer people use is called pooling. And so a pooling layer, the goal of a pooling layer is to simplify the model and carry like less data around. Essentially, it's going to say if the convolution, so something here or here or here, like in the same region, I don't really care where it is, like just tell me you found this in this area. Pooling is going to do this, it's going to say, you could do pooling, say 3 by 3, and it's going to say, if you find an activation in this area, just tell me you found it, and that's it. So it allows you, convolution allows you to look for patterns, and pooling allows you to simplify a bit the thing and say, like, if you found it on the left, that's good enough. I don't want to know exactly where it is. So the input looks like this, and I'm going to show you like how the model looks now that with the current state of my library. So first, I'm going to reset this, and I'm going to go to NIST CNN. I'm still going to use my library. I'm still going to load all of this. And so the beginning is like the same as it was before, because there's really not that much I can do about it. But so now the data set is a bit different. So I have now like 10 classes, like not just 0 and 1, but I have like, could be a 0, could be a 1, could be a 2. So I have like 10 things I want to recognize. So I'm going to have like 10 classes. The shape now is that we have a tensor, which is like 28 by 28. And there is like, for technical reasons, like 1, which is like, I have just like 1 level of depth, still floats. And the labels is like, I'm predicting something which could like have 1 of 10 values. Let me also show you the data set, because that might be helpful. So the data set is looking like this. It's pretty much the same as before, just like much more of it. So now, instead of having just 0 and 1, I have actually 10 labels. So this is called one-hot encoding. So what you see here is like I have like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it could be one of these things. And like in every row, like only one thing is a 1 and everything else is a 0. So it's called like one-hot encoding. Like this is saying this picture is a 1. This picture is a 0, 1, 2. This is a 3. This is a 3. This is a 1. So depending on which one is active, this is the one thing you're trying to predict. And otherwise, like these are pixels. I have like 800 pixels. Yep.
Did you need to pre-process the data from the standard list?
Yeah, I think I can probably do it without, but like I was too lazy to do that. So it's like I just like took the data and like dumped a file in a format which is convenient for me to work with. So this is what I want, and I want to learn from this by building a model and running it. So let's do that. Labels. Pop. So I described like I'm going to use 2 blocks. So I created a bunch of layers and a bunch of things in F#. So the first thing is I described like typically a convolution is going to describe like how large of an area do you want to scan. So in this case, like I'm creating like a template for my convolution, and the convolution is going to be something with the kernel, which is a width 3 and height 3. So it's really saying like scan the image 3 by 3, 3 by 3, 3 by 3. filters is currently 1, that's fine. And the strides are like, do you want to skip some of the things? So stride of 1 is saying let's scan everything. 2 is skip 2 by 2 by 2, and so on and so forth. Pooling is I'm pooling 3 by 3, so I'm going to summarize. Like, if you find something in this area of 3 by 3, just tell me you found one thing and that's enough. And now is like the piece I'm happy with is that part. So this is what I built. Is I can now build a model which is going to be composing layers together. So I can say now a layer is going to be first. I'm going to so this is coming from my library. If I do layer dot, I'm going to get things like standard layers, like a dense layer, a dropout layer, a scaling layer, all these things. And I can start to combine them with the pipeline. So I can say first, if you get inputs, I want you to take it and scale it down. So instead of 0 to 255, I want it to 0 to 1 because it's going to help for technical reasons. Then I want to add a convolution. So this is what I'm going to do here. Add a layer. Going to be a convolution. I'm going to take the convolution I created, and I'm saying like take the standard, just create 4 filters. So I'm going to create like 4 patterns to recognize. Then activate it. Then do a bit of pooling, and then I'm going to add another layer, which is again like a convolution. We're going to put 8 filters instead of 4, and I'm going to activate. I'm going to do the pooling, and I'm going to go into a dense model. And so hopefully, like the point here. Is like compared to the model I showed you before, where like one layer was like ugly as hell. Like this is pretty clean, and you can pretty directly see what the model is doing. So I inspired myself from what Keras is doing. And you can see input, do this, do this, do this, do this. The other thing which is really nice is like now if I want to change my model, I can just start to edit it here, put like 8 of them. I can insert other layers pretty easily. So it's like it will make it very easy for me to start to create and modify models. The other thing I created, what is happening? Oh, I see, like here. Yeah, here we go. And now is like the other piece I created, like instead of this whole garbage, is like I wanted to have something like a spec. I want to put in one line like this is what my model is about. So here I did like a sequential model is going to have input and output. So I'm going to say like features are this. Labels are this, the model is this is what I created, and this is what I want to classify, this is what I want to use as a metric. So like 5 lines, like done, clean. And finally, I also wanted to clean up a bit the readers. So it's like here I'm going to say like read features and read labels, but I made it a bit nicer. So I can configure the whole learning and say like, here's the mini batches you want. I want you to run like 50 times. So I put the device right there. So I'm trying to put things in like nicer blocks and don't have to do all the garbage by hand. And finally, I can just say like this is now you can plug it to this file. I use the feature stream I described before, and now I should be able to learn. Let's do that. Now this is going to be a bit longer than before because like instead of 64 images, I'm looking at 5,000. Or I can't remember how many, and I'm also working with the not 64 input, but like 800. And if you think about it, like the model I built above is like now is like I don't have one layer, I have like essentially 6 layers on top of each other with the multiple filters. So this is starting to be a bigger model. And you can see here that the numbers are decreasing, and the model is actually starting to look pretty good. Like my errors are going to close to 0. But like the overall point is not that it works. The overall point is like that getting to there was like much less painful than what I had before, which is really what I want. Now I have a model, I can save it. So if I save it, is like I'm going to get something like this. I'm sure there is a way to view it better. Like I know there is a standard for this, but like the model is really, the file I just saved contains everything. It contains the weights, contains the description of the expression. And so that model, now you should be able to take it, read it, and run it from Python, run it from C#, run it from F#. Then you can now start using this to make predictions. So which is what I'm going to do here. So now I'm going to load my model from disk. And I'm going to run it like on 500 images, which I just kept for validation. So the first thing I'm going to do is like, how good is this model? And so for those of you who have already seen like the NIST, like the digit recognizer. Then here what it is, I started running it on 500 images, and what I'm getting is I'm getting only 8 mistakes. So it's not perfect, but like it's not too bad. Like that's something like maybe 1.5% error. Like that right? Like that would be like 98.5% accurate. So it's and I'm using only 5,000 images. Like if I put more layers, I could get something a bit better, potentially. And the last thing I want to do here is I want to visualize stuff. And so the visualization, what I'm going to do is I'm simply going to take like a bunch of images and I'm going to make a couple of predictions. So again, very old school. So part of the point here, like this is the images you have in the data set. So it's like they're not clean, like they're quite messy. And let's look at what the model does. So was a 3 predicted a 3. It's not too bad. So that one was not too hard and we got it right. It's a bit harder, but I think got it right. 5 is always starting to be a bit trickier, but like, I don't know if you can see it on the top corner here, but like a prediction is correct. Like this was a 5 and predicted a 5. I would say like, this is starting to get a bit harder. 7, like even though there is it this much? Okay. Who would guess this was a 7? Like, and apparently the model got it right. Okay. A 5, pretty much I'm getting all of them right. Even this one, like you see, like you have like big smudges and stuff, and like the yeah, the model is working. So.
Do you have any feedback on the confidence observation?
What?
Do you have any feedback about the confidence?
I don't have it here, but you would actually get that because like I'm not displaying it here, but what the model does really is like you have like 10 outputs, and for each of them, it's going to give you either a percentage or like a value which indicates like how sure it is that which one it is. So right now is like I pick. Correct. Like right now is like I'm just looking at give me the one with the highest confidence. So this is the prediction, but like you get also something smoother, which is telling you like I think it's a 7, but maybe it's a 4.
Something like I cannot commit the process, but I have a 5% there.
Yep.
So I want to
yep.
5 and this happens.
You could do that because then you would see like how much it trusts that the answer is correct. Yep. Yeah. Yeah, look at this. Okay. This is a 2, and apparently it is a 2. Like, yeah, I'm going to I'm going to stop looking at this, but it looks like the model is working pretty well, and pretty spectacular. This is as bad as my doctor. Like, it's really really impressive. So okay.
Okay, that was way too good.
I didn't cheat. Like, this was really the data set. Like, yeah. So I mean, the fact that the model works is one point, and that's fine. Like, but really the bigger point, like the thing I cared about was to go from low level to something where I can actually compose models. And this is what I got with what I have now. Because like, if my model is not great, I can start to change very easily the architecture of my model, and I can test different models easily. And this is where I like a language like F# over Python, because I also get a statically typed language. So I get also help from the compiler to see like I did a mistake. I don't want to find like midway through 2 days of training that there was an error. I'm getting a runtime error. So like, it will tell me very early on that my model is correct or not correct. So conclusion is like work in progress. Like, it's usable. It's not finished. The sequential part is looking pretty good. Just needs to be fleshed out. Next up is like more layers on sequential, and I'm still working on the non-sequential part because that's a hard one to do right. If you want to contribute, if you're interested in feedback or anything, like the repository is like CNTK.F# on GitHub. The NuGet is actually there. It's like I'm not advertising it too much because it's work in progress, but it's there if you want to use it. It's horribly done. Like it's, I'm ashamed of the way I did the NuGet package, but it works. So. And another thing I wanted to mention is that if you're interested in deep learning on .NET, so I mentioned TensorFlow earlier. When I started working on CNTK, there was nothing on the TensorFlow side. Since then, is like there is a project called TensorFlow Shop, which is trying to build an API on top of TensorFlow. So I haven't used it yet. The main maintainer is like Miguel de Icaza, who is the like the main guy at Xamarin, like a very smart guy, and so I have no idea how good or how bad or how early it is, but like I wanted to mention it because like that project is there as well, and probably worth looking at. So this is what I got. I'm still Mathias Brandewinder. If you so I'm easy to find on Twitter. All these things. Like I'm going to do a shameless plug for the F# Foundation. So we do a lot of work for F#. It's the open source house for F#, and there is a Slack channel you can join for free. There is a Slack channel, and if you go there, you will find like many F# people, including me, talking about machine learning and all these things. And if this is not enough, I have stickers as well. So I hope to see some of you here. Anyways, like, this is what I had, so thank you. I hope you got something out of it. Questions? Once? Twice?
This is an option. This is not.
Sold. So let's have beers. I think is the next step. Yeah.
Okay. So we are going to the pub nearby. They make